In all AM or 3D printing processes, the construction by layers produces a surface roughness called the staircase effect, which is related with the thickness. In order to soften these shortcomings, there are some surface treatment solutions such as polishing, painting, application of acetone, or scientific or other specific products for this purpose. The XTC from On Smooth Company is economical, rectifies the staircase effect, and can be applied onto various types of surfaces such as plastic, paper, foam, cardboard, ABS, and PLA. After its application, parts can be painted or coated. The final aspect of glossy surface is shown in Figure 7b, prosthesis. The most common AM process currently available is the fused deposition modeling, presented in 1991 by Stratasys Inc., USA. This process consists of extruding a filament using plastic through a heated nozzle which is fed by a reel. Typically, these machines have two extrusion heads, one for the construction material and the other for supportive material. The simplicity of construction and operation of this process led to a significant growth of equipment sold by many companies. Since the FDM patent was dropped, the open source equipment emerged with an exponential growth as many users, designers, engineers, students, and others, called makers, built their own customized equipments. The Raptor hand prosthesis was the first one produced by the eNaBLE project. Despite all the innovation, it features some functional, constructive, and even ergonomic problems, considering also that its aesthetic aspect is not the same appealing one. Currently, the prosthetic hands provided by the eNaBLE project have some limitations and conceptual problems, can only be applied if the person has a functional wrist or elbow to be able to close and open the prosthesis. All fingers have the same size, which does not reflect a real hand. The existence of some little dissimulated hinges, wires, and rubber bands visible and unprotected. The elastics placement method and its durability, tightening of the prosthesis on the arm, restricted movements, and movements of the thumb vary differently from reality, among others. Thus, this work aims to contribute to the study and research of possible solutions to solve, or at least to mitigate possible solutions to solve these problems through the use of different materials and constructive solutions adapted to each amputation, always with the following main concerns: simplicity, low cost, possibility of being made into any 3D printer and assembled anywhere in the world. Product development. Introduction. In order to obtain a real case of the Portuguese child who needed a prosthesis and was available to participate in the eNaBLE project, some contacts were made with the amputees services of several hospitals. None suitable case in terms of age and level of amputation was found. Therefore, considering an orthopedic doctor's suggestions, it was decided to develop a prosthesis based on the same design concept of eNaBLE, but adapting the pre-existing metal part shown in Figure 4A, and that many amputees used to be able to fix the hook, also shown in Figure 4A. This was the way that they would perform some movements of their daily life, such as dressing, eating, cooking, among others. The main idea is to replace the hook with a prosthesis with dimensions and shape similar to the human hand to produce movements of locking and fixing, and flexible cosmetic glove may be placed over it. The prosthesis must be linked to the aluminum standard piece shown in Figure 4A. The manufacturing technology should be low-cost 3D printing, and the accessories used to link the various parts, screws, bolts, rubber bands, springs, and wires, must be cheap, simple, and easy to buy. The prosthesis development process is divided into 3 phases. The first phase concerns the anthropometric and anatomical hand study. The second phase is the functional study of the prosthesis. And finally, the third phase, and modeling, manufacturing, and assembling of the final product. Final phase, anthropometric and anatomic hand study. To the modeling process, it is fundamental to understand that the hand's functioning and know its dimensions. This phase is divided into 2 parts. In the first, measurements are taken as well as proportions of the wrist, fingers, and hand central part. And the second one is understand joints functioning in hand architecture anatomy. To obtain the dimensions needed for modeling, a hand plaster model of an adult man with a maximum length of about 210 millimeters was produced, using the same techniques used in orthodontics or sculpture. A mixture of water and alginate resulting in a paste, which is then applied on the workpiece from which one wants to obtain and mold previously placed in a box. After drying, the workpiece is taken out of the plastic and poured into a mold. Subsequently, the plaster was demolded to give a faithful reproduction of its desired object, as you can see in figure 9. Over this model, a color scheme was made and lines were drawn to indicate different parts of the hand and areas where the fingers flex and extend to facilitate measurements and allow the use of true dimensions in the study. Thus, it is possible and no further to make 3D models of smaller or larger dimensions by grading. Regarding the anatomy, the following points must be considered. The fundamental movements for the prosthesis functioning are the closing and opening of the hand. The articulation which allows flexion and extension in the 5 fingers is a hinge joint similar to a hinge. The connection between the thumb and the hand main body is implemented through a saddle joint similar to a cardan. These joints between the distal and medium fingertip of index, middle ringer, and little fingers are excluded because they are not relevant for the hand functioning. A single piece was designed to reproduce this part of the finger with an angle of 20 degrees. However, between the middle and the proximal phalanges, which joins the fingers to the hand's main body, between the proximal phalange and the metacarpal articulation, a 90-degree rotation must be considered. On thumb, among distal and proximal phalanges, as well as proximal phalange and metacarpal, there is also a 90-degree rotation. It was also considered important to incorporate more than one hold mode by the thumb with a rotation close to 54 degrees, which promotes 2 different closing modules that can be seen in figure 10. The hand has a few more aspects to consider in terms of form. Ringer and little fingers make an angle of 10 degrees horizontally and 3 degrees vertically. Finally, hand junction with the wrist makes an angle of 20 degrees to put in its functional position. These aspects must be taken into account during project and modeling and are summarized in figure 10. Second phase, functional prosthesis study. Joint system designs for extension and flexion of the fingers. The reference prosthesis Raptor Hand 2 has mechanical solutions to this articulation that in terms of aesthetic and functional point of view are not the most efficient. The elastics lose their elasticity in a short time and the hinges are often loosened in its axis. The objective is to develop a joint system considering the following assumptions. Mandatory flexion at 90 degrees, allowing the total fingers closure, blocking the rotation movement at the top, preventing hyperextension, hidden the components that produce the stresses, extension strength by a flexible hinge, flexion strength by a wire and spring. Facing the restrictions and constraints specified, some solutions were studied. In the first one, hinge is 3D printed on a flexible filament using it as a elastic. After construction and assembly, this concept was discarded because the movement produced by the solution is not smooth and precise, which is crucial to the prosthesis properly functioning. Get your history out and work on it. You've been walking back and forth. You're not done with that back page and a half.
He said don't do this, we're doing this tomorrow.
There's absolutely no reason to not get ahead of the game.
But he said he don't like when we're going ahead.
I don't care. Okay? I will email him in a little bit and tell him that. Okay?
Mm-hmm.
Another solution is based on the assumptions identical to the first one, but using orthotic elastics for the application of extension stress and the Teflon tube as the axis of the hinge in order to reduce friction. This solution also has problems. The support that ties and there is not enough space to accommodate all the components inside. The final concept is presented in Figure 11 and differs from the foregoing in some aspects. The extension stress is performed by a torsion spring and uses a brass pipe as hinge axes to avoid deformation by the force applied by the spring. Thumb rotation mechanism. The thumb finger is the most complex and difficult to understand in terms of movement which is capable. Since the objective will be to do more than one type of grip, the thumb may not always be in the same position and must be able to make a rotation. See Figure 10. After several interactions, the final one is presented in Figure 12 that has the rotation mechanism inside the hand in patent pending. The actuation is performed manually by the user other hand, similar to what happens nowadays in bionic prosthesis on the market. Flexion stress spring connected to amputee functional joint. The mechanical system is composed of wires, springs, and hinges. The opening and closing of the prosthesis by their user is achieved through the movement of the elbow and shoulder blades. This locking is due to the existing wire in the bottom of the prosthesis, which is connected to the elbow or to the shoulder blade by means of a guide tube in a similar way to the wires changes of brakes of a bicycle. According to a mathematical equation that defines torque, B equals F times D, being F the stress and D the distance between the rotation axis and the wire spring, it is found that greater the distance between the shaft and thread, lower the force needed for closing the prosthesis. Thus, the string is placed as far as possible to the shaft, allowing the user to use less force to close the prosthesis, Figure 13. In the final prototype, D is 9 millimeters. The basic requirements for the choice of wire which produces the bending stress were greatly reduced elasticity level, ensuring a good response in tension during stress application and wear resistance. Initially, a nylon spring was tested from which was obtained a good response in terms of mechanical properties, but low wear resistance. So, a Kelvar string was selected, consisting of 8 filaments crossed with a thickness of 0.2 millimeters, able to withstand tensile forces of up to 13 kgf. Extension stress. The force which counteracts the hand locking is accomplished by the torsion spring. After several studies and tests, it was found that the most suitable spring is made of hardened stainless steel wire with 1 millimeter in diameter and a stiffness of 14 N millimeter to the negative first power. Third phase, modeling, manufacture, and assembly of the final product. The modeling of the final product integrates the constructive solutions described in the second phase, considering the dimensions and functional concerns studied in phase 1 and seeking the low-cost production process based on additive manufacturing, the modeling software used for SolidWorks. Owing to the necessity of creating space for the passage of the wires which converge to a single wire, the main frame is composed of 2 parts. The main structure, main body hand, produced in solid filament, and a lid in flexible filament. The path of the string was designed so that they are all connected in the middle of the main body through tunnels in order to be joined with a single wire. The main wire will connect to the elbow and the shoulder, which are functional linkage of the amputee, allowing hand closing by force F. The main structure of the prosthesis, main hand body, is designed in order to be printed vertically, as shown in Figure 15, without the use of supports. The highlighted areas indicate some of the situations. Because of their rounded shapes, fingers had to be split into 2 halves, allowing printing without supports. Figure 15. The first cut was made in the middle finger, also sectioning the existing tunnel for the spring path, which causes a problem. During the pull, the string we're going to skip a couple of paragraphs. That's just talking about the diagrams. So it says, this research work was developed on the scope of a master thesis in industrial design. We arrived to the final prototype but unfortunately we did not find a patient to test it. Figure 16 BC shows images of the test grabbing a plastic bottle and a pencil. The developed prosthesis was obtained through an iterative process that considered functionality and price. The final product depicted in Figure 16 was produced by a final cost of 115 euros, considering 28 euros in standard components, the screws, nuts, springs, bearings, and 127 euros for parts obtained by additive manufacturing. Although this product has a higher cost than the ones of the eNavel project, which was between 30 to 50 euros, the extra functionalities introduced, like the movement of the thumb and dissimilar fingers motion, robustness of thicker parts, better grabbing of object achieved through the use of flexible polymer, and more appealing design seems to justify the increase in cost. Although the price obtained, the prosthesis has 4 times lower cost than the equivalent prosthesis shown in 4. Conclusion. It is possible to manufacture functional low-cost hand prosthesis through 3D printing. In addition, the components required for assembly, the product developed the world because they are not customized. The solutions studied and presented solve some of the design problems of eNavel prosthesis, such as improving the aesthetic aspect, thumb movement, finger dimensions, and functionality close to reality, better adaptation and adherence to objects due to fingertips and hand palm on flexible material, and all components are hidden inside the hand. Therefore, it can be concluded that this work contributes significantly to the success of the Project eNavel.